Well, I found out you can only have a YouTube video going for 10 minutes. So this is the second part. Where I left off was what's in section 3.4, the second derivative test, or maximums and minimums. We've used the first derivative test where you looked at whether the derivative changed from positive to negative or negative to positive. The second derivative test, you don't do it over a region, you do it at a specific point. Okay, for the second derivative test, if at a specific point you find out that the derivative is 0, let's say you find out that 4, the derivative equals 0, and you put 4 into the second derivative and you get a negative number, that tells you 4 has to be a relative maximum. Okay, here's the basic little, graph. It's concave down, so the second derivative is negative, but right at that point, the first derivative is 0. There's a horizontal tangent line there. Okay, on the other side, if the derivative equals 0 at a point, and the second derivative is positive, which means it's concave up, okay, right here there's a horizontal tangent line, but at that point, the second derivative would be positive because it's concave up. It has to be a relative minimum. If they both happen to equal 0, it's probably a point of inflection, but you cannot make any specific statements at that point. Okay, what I'm going to do is put up the problems from section 3.4. I'm going to leave, there's 4 pages here. I'm not going to talk my way through them. I'm just going to maybe kind of briefly go through. You may want to take a picture of them because they'll only be up there for a minute. And then you can use it to compare when you actually do your homework. So I'm taking this down. Here's the first page from homework in section 3.4. You may have to do this in 2 separate parts. The first one just has some basic little graphs when you look at your homework. The first one, number 3, it'll be the derivative is positive because it's increasing, but the second derivative is negative. It'll be concave down. Number 4, first derivative is negative because it's decreasing, but it's concave up. Number 5 and 6, and I think number 7, they want you to find places, the regions over concavity where it's concave up and down. So I'm going to take this down a little bit. Again, you may want to take different pictures at each of these points. There's number 5. You take the derivative, the second derivative. Second derivative is 2, so it'll always be positive no matter what x is. Therefore, it's always concave up because the original function actually is a parabola. Number 6, you take the derivative, the second derivative, set the second derivative equal to 0. Solve it, you get x equals 1. Taking a value on each side of 1, I picked 0 and 2. When you put 0 into the second derivative, 6 minus 6x, put 0 in, you get 6. That tells me in that region where 0 is included, negative infinity to 1, where that second derivative was 0, it will be concave up because the second derivative is positive. On the other side of 1, from 1 to positive infinity, if I put in a number like 2 into the second derivative, it's negative, telling me it's concave down. For number 12, you have to use the quotient rule. The second derivative ends up being 30 over x minus 7, the quantity cubed. At 7, back here at the derivative will be undefined at 7, which means it's a critical point. The derivative won't be 0, the derivative will be undefined. There's way back in the original function, something we did back in chapter 1, there'll be a vertical asymptotic line there, which means the derivative would be undefined. So there will be a critical point at 7. So you check each part or each side of 7. I picked 6 and 8. When you put 6 into the second derivative, you get a negative number, which tells me, therefore, from negative infinity to 7, the function will be concave down. For 8, on the other side of 7, you end up with the second derivative being positive. put it into the second derivative, is positive, and therefore it's concave up. Okay, hopefully you can take pictures or go through this several times or pause it on this. I'm not sure how you're going to do it. Okay, the next page, number 17, same idea. It's a cubic function. Take the derivative, the second derivative, set it equal to 0. Here they want you to find regions of concavity and points of inflection. It must change concavity to be a point of inflection. Doesn't matter if it goes from down to up or up to down. Maximums and minimums, it mattered which direction it went, but a point of inflection is anywhere it changes concavity. Down to up or up to down. Okay, the 3, 0. That 0 here, to get the ordered pair, you put 3 back into the original function. Now it happens to be the second derivative will also be 0 at 3. That's just coincidence. To get the ordered pair, once you find where the second derivative is 0, to get the ordered pair, you have to put that number back into the original function. Here it will happen to be 0 also. The next one is kind of a mess. You have to use the product rule, the quotient rule. When you get to the second derivative, it ends up you're going to go through a whole bunch of work to find out that there's no points of inflection, but there is it is concave up from -3 to infinity. At -3, anything less than -3, the function would be undefined because here in the original function, it gives you imaginaries. So here, final answer, there's no points of inflection. It's concave up from -3 to infinity. Okay, I'm going to have to get through these pretty quick because I see I'm getting close to the end of my time frame again. Here's 34. I'm not going to say a whole lot about it. Here you're looking for points of inflection. Or actually, I take that back. They want you to use a second derivative test. You take the derivative, set it equal to 0, and find out where the derivative is 0, which is at -2/3. You put that value into the second derivative. The second derivative is always positive, no matter what x is. Therefore, the derivative is 0 at -2/3, but positive at -2/3. Therefore, it's concave up, but a relative or a point where there's the derivative is 0. So the graph kind of looks like what's up here in the corner, concave up and a horizontal tangent at -2/3, so it has to be a relative minimum. 43, both the first and the second derivative will be 0 at 3 pi over 2 and 7 pi over 2. Therefore, there's neither a maximum or a minimum. Probably will be a point of inflection, but you're not checking for that. 53, they give you some information. F of 0 and f of 2 equals 0. Those are your x-intercepts. F prime of x is greater than 0, which means it's increasing when x is less than 1. At 1, the derivative is 0, so there's a horizontal tangent. F prime of x is less than 0 for x is greater than 1. It's decreasing, and it's always concave down. So the basic shape of the graph, which is what they want you to do, make a quick little sketch, will be this little part. Okay, last one, and this has a lot of algebra in it. I wish there was an easier way. You may want to take pictures of this because this takes a lot of algebra. I've got about a minute left here before it shuts out on me, so I'll just kind of leave this set. You'll take the function, you'll take the derivative, the second derivative, use the fact that there's an inflection point. Therefore, the second derivative is 0, and you can find the relationship between B and A. There's a maximum and minimum at 3 and 5, and therefore the derivative is 0. And I kind of wrote as much as I could here, but this has a tremendous amount of algebra in it, and unfortunately, I think there's one of these on your quiz when you get to the Module 5. I think it'll be, well, maybe, yeah, Module 5 quiz. One of these will be on here. The final functions up here in the side, 1/2 x cubed minus 6x squared plus 45 halves x minus 24. I know I moved it around. You may want to take pictures. I'll leave it here for a second because I've only got a few seconds left and it's going to shut off on me. There's the top part. There's the bottom part.